Okay, so I wanted to add this little piece on carbon cycle and global warming targets, carbon emissions and global warming targets, because this discussion about emissions gap and how many years we have left to save ourselves comes up a lot, which is not considered to be a good idea by everybody, especially social scientists worry about this narrative about having only 7 years to left to save ourselves because they can be misused. It's not even very reliable because of the uncertainties in the system and in the carbon cycle and so on. But let me use this figure to get to that point. So we looked at this before in the second chapter, I think, probably, but this just shows the anthropogenic fluxes averaged over 2010 to 2019. In the first figure of this chapter, we looked at, I think, 2009 to 2018 or so, but it doesn't matter. As we said, the atmospheric amount reservoir size keeps increasing. This is at 860 gigaton carbon per year with a flux of plus or increase of plus 5.1 gigaton carbon per year. There is uptake, there are exchanges that I mentioned, there are reservoirs that are big, small, average, and there are time scales. So this is the anthropogenic flux here. There are buried reserves in gas, oil and corals that we saw. There is a volcanic flux. So we have fossil fuel CO2, land uptake, land use change emitting a little bit, ocean uptake of 2.5 gigaton carbon per year, and so on. What do we do with it? We compute the annual flux into the atmosphere, which looks like this. For example, averaged over 1850 to 2018. This is now cumulative. So cumulative changes from 1850 to 2018 in terms of gigaton carbon from coal, oil and gas is here. We added another 2005 from land use change and so on. We took out land use uptake, so the land use is a net difference of these, and we took out ocean uptake here, and this is the this is plus, so you have added atmospheric concentration, and this is the budget imbalance. Okay, so this is just the same thing looking at in another way. So these are the mean fluxes for 2009 to 2018. Again, we keep looking at different periods based on when the calculations were done and what data that was used. So this is similar to what we just saw here. So 9.5 gigatons carbon over this period in terms of flux, with land use and other ocean uptake, land uptake, and atmospheric CO2 increase with the residual. Why do we worry about cumulative carbon? It turns out that the warming that happens globally is almost linearly proportional to cumulative CO2 emissions since 1850. Okay, so which means when we make future projections, these are the future projection scenarios called shared socioeconomic pathways, with numbers here 1.9, 2.6 to 8.5 being the radiative imbalance at the top. So that's the net forcing resulting in each of these scenarios. For example, SSP 5 8.5 is a particular shared socioeconomic pathway which results in a net radiative forcing delta F that we talked about of 8.5 watts per meter squared. This is usually referred to as business as usual. It's the highest we expect if we do nothing in terms of policies, renewable energy, changes in behavior, everything we do that is going to increase emissions. And then you have various other scenarios that provide various other levels of radiative forcing, and SSP 1 to 5 have various details in them in terms of how technology will change, how population will change, what kind of policies will be adopted, what kind of governance, what kind of sustainability goals will be set by the global community and each player at state level, for example, and so on. So the near linear relationship between the cumulative CO2 emissions and global warming for 5 illustrative scenarios until 2050. What do we do with this? If we know how much CO2 we are emitting each year, and if we know that the warming is almost linearly proportional to additional carbon. Why additional? Because this is with respect to the base we started with at 1850. So the warming is with respect to 1850 to 1900 average. So these are the anomalies above that average, how much we are warming above that average. So you can see here the future cumulative CO2 emissions differ across scenarios and determine how much warming we will experience. So these are showing the various levels of emissions by 2050, 2030, 2040, 2050. So if we know how much we emit per year, and if we want to limit the warming to a certain level like 1.5 degrees centigrade or 2 degrees centigrade with a certain probability like 67% with respect to this baseline, then we can say how much more carbon we can emit, because we know how linearly it accumulates to warm to the required level. So that difference is often used to argue that there are only so many years left. But we already saw how many uncertainties there are in the carbon cycle. It depends on the model you use. It depends on so many other things. It depends on the ocean doing its thing, the land doing its thing, and the energy doing its thing, and so on. So not everybody agrees with this idea of taking remaining emissions room and converting into number of years left to save humanity and so on. I'm definitely not a fan of that argument or that line of saying how many years are left. So here is future warming under different zero emissions scenarios. We are again starting from 1880 with respect to 1880 to 1899 baseline. The baseline can be changed. It doesn't matter. The story remains the same. The science remains the same. So here's the observed temperatures. Zero CO2, if we zero it out by 2020, which is already late, then we will go into this climate sensitivity and committed warming. So you can see that it will increase by a bit even if we stop the emissions, because cumulative carbon is still there. If we go zero greenhouse gases plus aerosols, because it's not just CO2, we have methane, nitrous oxide, CFCs, HFCs, land use change, cement, steel, and so on, plus aerosols, then the warming will exceed 1.5 degree, for example, here. If you have that's zero, so here we are zero GHGs and aerosols. This is zero CO2 and aerosols, so it doesn't include other greenhouse gases, then you're going to overshoot, and so on. And so this one is zero greenhouse gases without aerosols. So basically this is saying that just worrying about net zero where CO2 is the only target is not a good idea, because you have to consider other greenhouse gases as well. So here is how the remaining and consumed carbon budgets are typically portrayed. For 1.5 degrees centigrade, with only 50% likelihood of not exceeding it, you have consumed 2475 gigatons, and we have only left 420. So you take per year emission of 40, and that gives you, I don't know, some 10-12 years of remaining time to hit this target. 1.7 degrees warming allowed with 50% likelihood gives you more room to emit some more carbon. If you jump into 2 degrees centigrade with a 50% likelihood, you get a bit more room to emit more carbon. Are these goals really scientifically robustly determined? Not really. These evolved out of economic calculations by Bill Nordhaus in the 1970s. You adapted it, Stern Report adopted it. Then we retrofit the impacts that could happen at 2 degrees centigrade. Then we said it would be too dangerous, so we lowered it to 1.5 degrees centigrade. So it's also not clear what do we mean by 1.5 degrees C. If we exceed it for 1 year and come back, does it mean anything? If we exceed it for 10 years, then what happens? So it's not always clear what we mean. Plus, a lot of things are already happening in terms of warming, humidity, extreme events, sea level rise, glacier melts, health impacts, and so on. So nothing dramatic will likely happen when we cross these thresholds. So people may just think, what the hell was all the hoopla about? So we have to be very careful about these things as well. So here is another way to look at it. We have been emitting here going into the future. This is from 2010 or so. If we had no climate policies, this is the estimated warming we would get by 2100. With the policies that existed in 2010, we would bring it down to here, 2.7 to 3.1 degrees centigrade, from 4.1 to 4.8 degrees centigrade. The pledges and targets brought it down to would bring it down to 2.4, but to reach the 2 degrees C or 1.5 degrees C pathways, we will have to seriously draw down carbon, but that we are already late anyways, and COP26 has had people redrawing this to say what the emission gaps are. So those are typically referred to as emission gaps. So going from gigaton of carbon here to gigaton of carbon here is the emission gap in achieving these targets. So there are lots of issues here, but the main thing is that the best strategy we can think of is to decarbonize the whole system. Don't worry about efficiencies and this and that. Just make sure that all the energy and all the other agricultural activities, transportation, building, everything we do does not emit any carbon. But does it mean we emit some carbon and take out some carbon, or does it mean we don't emit any carbon at all? So what does net zero mean? Those are all kind of difficult questions, but negotiations go on, and we are not really on target to achieve any of these as of yet, but you have to keep your eyes on how the electric vehicles are growing in market share and technology and efficiency, how solar and wind energies are going up, nuclear, hydro power, fusion, how we are improving buildings, transportation, flying, appliances, everything we do. So there is a question of reducing emissions, and there is a question of not emitting at all. So they are not always the same, but hopefully we will keep working hard at this and reach the goals that are not necessarily 1.5 or 2, but things that are not dangerous for anybody, because a global warming of 1.5 degrees centigrade with any probability doesn't tell you what will happen in your backyard. It just says that globally this average mean temperature is accomplished. Plus, global warming creates winners and losers. For example, warming may make Siberia into a rich agricultural land, and Russia would be very happy with it. So not everybody will necessarily lose with global warming, even though the summer and the year 2021 has produced so many extreme events across the globe in poor and rich countries that maybe nobody will be spared in the end. So we have to keep going with this and look for solutions. Okay,